All right, welcome back, everybody. We're going to do something, well, you don't know it's different. Only I know it's different. In this week's lecture, what I had planned and have done for every single year was to cover induction. Well, actually, I cover magnetos, induction, exhaust, and turbocharging systems. But I'm changing it for two reasons. Reason number one, in talking with Larry Johnson, he covers exhaust systems and intake systems to a much larger degree. And even my notes say it's a lot of material. It's I can't even cover this in 7 regular days. So on campus. So that means I can cut out turbos and induction systems, which makes my life a lot easier. We will have to talk about it just a little bit so that you understand induction and exhaust systems, because you can't understand turbos if you don't understand those, at least a little bit, but we don't have to go into how they're built and all this other stuff. And we've covered a lot of the basics already, especially on both of them. The other thing that I normally cover is, pull this up, slideshow from beginning.
Hey, Kevin.
Yeah, I know I'm not probably sharing my screen yet. Am I sharing the screen? Not yet. Share screen, screen 2. Go ahead.
Yeah, are these system part of the Q&A too?
They are, and I should probably go into the, not probably, I need to go into the Q&As and change them, but I don't think I can because a lot of you have already completed the Q&As. So it's good. I'm going to leave them in the Q&As. That's what I'm going to do because it's not a whole lot there. And we need to cover it. You need to understand them. So I'm going to leave it alone. I'm not going to cover Magneto installation right now because I believe that this is one of those things where it's best where I actually show you how it's done. And normally I would take you into the lab. I would have everybody gather around. We would go through it and I would explain what's happening and it would make a lot more sense. As it's now, I'm going to be talking about something that you're just not going to have a grasp of and it won't make sense. I'll be talking about how to time it and this and that, you know, well, like, can I see it? I was thinking about doing a video, but unfortunately I don't have the equipment that you guys have in the lab. So I can't go get it. So it wouldn't make any sense. I was just going to use my airplane and do it, but I can't. So we're going to we're skipping a lot of this and that's going to bring us right into exhaust systems, but kind of go through. So yeah, intake, there's all the stuff you're not going to get on magnetos. And intake systems we're not going to cover. That's an airbox. Said Larry's going to cover all of this stuff. And let me think. These are non-turbocharged exhaust systems. This is a stuff called scat tube. That's another thing that you should not Google is scat tube. People are disgusting. And then we're going to get into turbocharging systems. And when we get into turbocharging, as far as induction goes, actually we'll get into turbos in a little bit. So I think that's just a pretty picture right there. So having said all that, where are we going to start? Well, we're going to start with not quite turbos, but turbocharging and supercharging to be exact. So you guys ready to go?
Yep.
Sure.
Yep.
Uh-huh.
All right. All right, I'm getting ready. All right, turbocharging and supercharging. Turbocharging. Turbocharging and supercharging. And let me see here. One of the things that we're going to have to do is we're going to have to set up some, I guess, classroom nomenclature and definitions, because out in the industry, things are a little weird and it's hard to talk the same talk. Well, one manufacturer calls it one thing, one calls it another. And within that, you have to kind of work around. So I'm just going to tell you right now, when I talk about in the class to keep things simple, supercharging, or if I talk about, I should say a supercharger or turbocharging or turbocharger. I'm trying to figure out how I can explain this without you knowing where we're going already. So I would just say a supercharger, it's a thing. All right. So if I talk about a supercharger, I'm going to pull my PowerPoint back up. This right here, what you're seeing right here, that is an internal impeller. As you can see, it's a centrifugal supercharger of Bristol Centaurus radial aircraft engine. Pictures in there because I think it's just gorgeous. I would have this hanging on my wall. It's very pretty. So when I talk about a supercharger, I'm going to be talking about something that is driven off of either a belt or gear driven, and it has this sort of impeller. And we'll get back around to this stuff right here, but here you can see this has an internal impeller right here. You talked about these impellers with fill, centrifugal compressors in turbine engines. Well, it's going to be the same thing. It's just now going to be used to compress air going into a piston engine. So this is what I will call a supercharger. It's something that's mechanically driven off of a belt, a gear drive, something like that. This right here is often called a roots type blower. They're also used for on some aircraft for cabin pressurization. But you've seen this on cars more than anything, where these impellers go around, and it's actually what do I want to say, a constant displacement compressor that compresses air. And this one here, and I'll come back around to it, but it's driven off of a belt. So that's a supercharger, and the one before is a supercharger. And then we're going to get into this thing right here, which is a turbocharger, and it is run off of exhaust gases coming through here. So there's no mechanical linkage whatsoever to make this go. It's simply air blowing through one end makes air blow through another end, and I'll explain how that works. So I'm going to call this a supercharger. Okay, so I have turbocharger. I'm sorry, this turbocharger, and the other thing is a supercharger. So now you can say turbocharger, supercharger. Now if I say it in those terms, it's a thing. Okay. Now it's going to get more complicated because now I can talk about supercharging versus turbocharging, and then you actually get into turbo supercharging. And so if I talk about turbocharging, clearly uses a turbo. Supercharging in a perfect world would mean that you're using one of the gear driven or belt driven items to put air into it, but it doesn't work that way. In aviation, they will often say something is turbo supercharged. And you're thinking, okay, so that means it has both things? No, it doesn't. So to keep it simple, a turbocharger is the thing that runs off of exhaust gases. And for the most part, manufacturers, when they say their engine is turbocharged, it just means that the turbocharger boosts the air pressure to atmospheric, standard atmospheric. So it never goes above so if you had a turbocharged engine sitting right next to a normally aspirated engine, they both can do the same thing. Neither one of them has an advantage until you start going up in the air. We'll talk about that. But then they say it's turbo supercharged. That means that they actually take the turbocharger and boost the air pressure up beyond atmospheric. So if you can kind of keep that in mind, and I'll try and make it clear as I go through this, but if it's not, just kind of pull me back and go, hey, wait a minute, is that, what exactly are you talking about? So, but again, I'll try and make that more clear as we go along.
Yeah, I'm
so, okay.
confused already.
Yeah, I figured you would be. So, well, if you get confused more later, then you know why. So we'll just start slow and then we'll work our way into it then. So I'll assume you know nothing yet. Turbocharging and supercharging. Here we go. Why do we need to do this? What's this all about? Well, first we're going to talk about air and density. Air and density of the air. All right, and density. So we know that at sea level, so sea level pressure on a standard day, is, what's standard day and temperature wise? 59 degrees F, 15. Nobody cares about Celsius, sorry. And it is 29.92. What's that?
Inches of mercury. I was gonna finish. I was gonna say inches of mercury.
Oh, well, thank you for helping me there. Or 14.7 PSI. PSI. And again, I'm going to round up to 30 inches Hg. All right, let's see if I can do this without confusing everybody. Then we can talk about Boyle's law. Boyle's law. And anybody want to, who is this named after? Great, Dr. Charles Law.
Charles.
I was going to say Henry.
Was not. All right. So it's in any sample of gas, the volume is inversely proportional. It is, oops, that's an is inversely proportional to the absolute pressure, if the temp is kept constant, if the temp is kept constant. All right, so what does that actually mean? If the volume is inversely proportional to the absolute pressure. I guess another way of saying this is we're going to talk about cylinders, and inside of these cylinders we have an absolute volume. The temperature is not kept constant, so it kind of throws it out, but hey, this is Boyle's law anyway. So any sample of gas, the volume is proportional to the absolute pressure. So if we can increase the pressure, we have also increased the volume, which probably intuitively, you guys already know that. So that's what we're going to try to do. We need to increase the pressure inside of the cylinder. And what is that going to do for us? Well, it's going to increase the volume, which is according to Boyle's law, but why do I care? Why do I want to increase the pressure? Why do I want to increase the volume?
Volumetric efficiency.
Well, I won't say you're wrong on that, because turbocharging, supercharging, absolutely, it's a compressor that is pushing air into the cylinder rather than allowing the cylinder or the piston to draw it in. So number one, you are going to dramatically increase your volumetric efficiency right there, because instead of being sucked in, it's blown in. It is pushed in. But
because of less density then?
Well, we're going to increase the density.
More air, more fuel, so you can get more power.
Remember this thing? Planck?
So trying to wrap my head around this, when you mean inverse proportional to the absolute pressure, so take, for example, like xenon gas and like just regular air and put them in like a cylinder and then increase the pressure and keep the temperature the same, they're going to fill up the same amount of the cylinder?
Well, that's a weird way of saying it, but just think of it this way. If I've increased the pressure, it means I put more air in, therefore the volume is bigger, right?
Mm.
All right, do you remember Planck? What was Planck all about?
Power.
It was what?
How, like horsepower?
It was horsepower. And anybody remember what it all was off the top of your head?
Pressure. Numbers of cylinders.
Yep.
Length of the stroke.
Length.
Number of cylinders.
Length.
Length of stroke.
Stroke.
Area of the piston.
Area of the piston.
Number.
Number of revolutions or number of power
RPM,
strokes.
that was RPM. Okay, so if we can increase any of these, we get more horsepower. So if we can increase the pressure, we're going to increase the horsepower. So that's what this is all about. Increase the pressure, which increases the volume of gas in there. If you increase the volume of air, which we call the gas, then you also have to add more fuel to it. And so now you have more gas, more fuel, more pressure, more power. All right, so a couple of, let's see, points I've got here. So 13 cubic feet of air at 14.7 psi equals 1 pound. Equals 1 pound. At 10 psi, okay, now we've gone down. We had 14.7, we have 1 pound of air. Now at 10 psi, same thing, 10 psi. At 10 psi, we need, we has one E there. We need 15 cubic feet. To equal that same 1 pound. 1 pound. I probably could have wrote it the same way. 15 feet of air at 14 psi is 1 pound, or 15 cubic feet of air at 10 psi is 1 pound. So you start dropping that psi down, which is what happens when we go up in altitude, right? Which I'll say in a minute. Then you're going to get less air in the cylinder. Less air in the cylinder again is less power. So we need that air back in there. 15 cubic feet of air at, we'll say 20 psi. At 20 psi is 2 pounds. So right here I have the same cubic feet. 15 at 10 is 1 pound. Double it. 15 at 20, you have 2 pounds. All right, so I say that just to say that as we add pressure, we're adding, as we add more air in, we add more pressure. More pressure is more power, and more power is good. All right, but we also know this, right? As altitude, A-L-T-I-T, altitude increases, as altitude increases, both the pressure and density decrease. Which is to say, as I go up in altitude, I'm going to lose horsepower. So if I take my airplane, a Cessna 150 with the O200, it's rated at 100 horsepower. Where am I going to get 100 horsepower and when?
In the cylinders at sea level?
Say it again.
In the cylinders at sea level?
Okay, I like that answer. So you're far more specific than I was even thinking. But yes, well, it depends. So if it's brake horsepower, then it's outside the cylinders. So the idea is it gets 100 horsepower at a standard day at sea level. So I take off and I climb 1,000 feet to pattern altitude. Do I have 100 horsepower left?
No.
I already started losing it. The higher I go, the less horsepower I get. So that is not good. Let's see here. At sea level, what do I have here? At sea level.
And that would be at a given RPM, correct?
Max RPM.
But
So
in
if
reality, you don't get 100%.
No, it's rated at 100 horsepower. So really, I really should be getting 100 horsepower on the ground, standard day at sea level, brake horsepower. Now, thrust horsepower is different. Remember, thrust horsepower takes into the consideration what's usable out of the propeller. But if I measure it at the hub of the crankshaft, then absolutely, yeah, I should be getting 100 horsepower. And the engine gets a little bit tired and starts to wear out. Well, I'm going to get a little bit less. And if you remember, the way that I determine with a fixed pitch propeller, if I get my rated horsepower, is it's going to fall through that static RPM limits that are on the type certificate data sheet. So every time I do an annual inspection, I put my feet on the brakes, find a place where there's no rocks around the ground, go to wide open throttle, and I sit there with the airplane not moving, and it's got to get that static RPM. It's whatever RPM I get, and it should reach this certain, not exceed a certain limit and not go be under a certain limit. If it exceeds it, usually means I have the wrong prop on it, and I'm creating more than 100 horsepower because the RPM went too high. That's bad for it. Go the other way usually means that either you have the wrong prop or you're just losing power. Now, okay, so at sea level, So at sea level, I should get all aircraft engines should get 100% power. And let's see, I used here. I said let's consider a Pratt and Whitney 985. Why? Because I happen to know that one has 450 horsepower. That's 450 horsepower. So on the ground, I probably shouldn't have used this one for reasons I'll tell you in a minute. But Pratt and Whitney 985 or whatever, just it was a bad choice. That's actually a supercharged engine, so this doesn't count. But anyway, let's just say some engine that is not supercharged, not turbocharged, on the ground, it has 450 horsepower. All right, so I take that same engine, whatever it may be, and I go up to 10,000 feet. So I go to 10,000 feet, I am only going to get at that point, the maximum I can get is 75% power. So if wide open, it's going to be only 75% power. At 75% power, that is left. Now I have 337.5 horsepower. So that's all I've got left out of it. So how much did I lose? Well, if we did the math real quick there, we have a loss of 102.5 horsepower. That's an entire Continental 0200 and then some. And 10,000 is not that far. I mean, it's further than I'm going to go. All right, at 20,000 feet, an aircraft engine that had normally 455, well, any horsepower, you're going to be down to 50% power, which right now is down to only 225.
And that's at wide open throttle.
That's, yep, wide open throttle, give it all you got. If I could make it to 30,000 feet with an engine that didn't compensate for this problem, I'd be down to 33% power, which would only give me 148. And by the time I got to 40,000 feet, which I don't think would happen, I would be at 25% power, which would only give me 115 horsepower, which this giant 450 horsepower engine is now down to the equivalent of a 152 horsepower. So you can see that what the density in the loss of pressure actually does to an engine and how quickly it can happen. What's the highest mountain range you can travel across in the United States? Is it like through Pikes Peak or someplace like that? Somebody know? You guys are a lot of good.
Harry,
I thought it was the Rockies,
There you go, Rockies, kind of going through what, Colorado or something like that?
somewhere in there.
What's the altitude you take your, so what's the highest potential to bring your car to? Nobody knows.
Right now.
You're
10?
looking it up.
10 or 12,000?
12,000. All right. Well, we could take this if you go up to Tahoe. Now, if you go up to Tahoe through Donner Pass, what do you hit there? 8,000?
The top of
Yeah,
Donner's like
over 7.
almost 8.
Okay, yeah. And then the top of Heavenly Valley is somewhere around 10,000. So even right here in California, you can drive your car up there around that. And
unless it's a Tesla, right?
this does not count for Harry. That's why he doesn't care. So
Constant torque.
I know. All right, but let's see. So let's see, what's 300 horsepower?
It was about 14,000 feet. I looked it up.
14,000?
Highest one in Colorado is like 14,000 feet.
All right. So what do you want to say? Just extrapolate. That's between 10 and 20,000. So what about, let's say 60% power?
Yeah.
My car's only got like 110 horsepower, so that's like what?
All right. That's a good one. So 110 times 65%. So you're down to 71 ponies left.
Better turn the AC off to try and make it up the rest of that way.
That's right. And your AC takes probably 12 horsepower. I don't know. I made that number up. So yeah, so you can see what's going on here. So that's not going to work out well. So how do we fix this? Well, here's where turbochargers come in. And more cars, of course, are coming out with turbochargers. But let's talk about this one first. Heat. Heat has the opposite effect. The more heat you got, the worse it gets. But okay. So this one's Charles' law. Charles' law. Invented by the famous Jeffrey Charles on this one. So if a temperature of a given quantity of gas is raised and the pressure is held constant, the gas will expand. Gas will expand in proportion to the absolute temperature, in proportion to the absolute temperature. In other words, hot air expands. I'll put that. So in other words, hot air expands. And for the same volume of air, would you then have more or less weight, more or less density?
You would have less.
There we go. So in other words, hot air expands. So for a given quantity or volume of gas, as temp goes up, density goes down. The density becomes less. So the air weighs less. So just like with, I'll write that one. So this is why carb heat shows a loss of power. You put hot air into an induction system, you're going to lose power. Pikes Peak, I was right. It was Pikes Peak, huh? Car can go as high as 14,000 feet. All right, so heat is bad, right? Heat causes inside the induction system. So if we could somehow pack in, we'll just make up some numbers here. We could pack in 20 PSI, but then we heat up the air. We are going to, Matt, what the hell are you doing? Going for a walk today, buddy? Have a look over here. He's like looking up in the sky. All right, distractions. Yes, he is going for a walk. Now he's walking through his living room. So if we can manage to...
The highest airport you can go to, it's 14,800.
Okay. All right. So we pack in a certain amount of pressure into the intake system. We can get that pressure in there, but if the air is really hot, the density goes down. So heat is a bad thing. Heat is bad. Pressure is good. We want more pressure, but heat becomes a bad thing. And at a certain point, we could actually get enough heat inside an induction system that we can actually start lighting off fuel. So heat is a limiting factor of some of these turbocharging systems. So excessive heat. So I want you to remember that as we talk about this. It's like, well, why don't we just go more? Why can't we just compress more? Because you can't, because the heat starts to cause problems. So excessive heat from, I'm just saying compression. And not compression from the cylinders, because that's a whole different type of heat. You're getting heat there because you're actually using a spark plug and gas and you're lighting it on fire and creating that. But heat from compression, like an air compressor or something like that, is not desirable. It is not desirable. D-E-S-I-R-A-B, desirable. So if you actually mess around with air compressors very much and you are using an air compressor quite a bit and you put your hand on the tank, you'll notice that the tank gets pretty hot, or at least it gets warm, because when you compress air, it heats, it gets hot from the friction is what the word I was looking for. All right, so this lowers the turbo effectiveness. Enough heat out of the turbocharger can cause detonation. And about where? So also, let's see here, compression causes heat. Compression causes heat. And if the air is hot enough, and that'd be about 500 degrees Fahrenheit, the fuel will ignite. All right, so what I'm talking about here, because my notes maybe don't make a whole lot of sense if you weren't really watching it. We have a problem with an engine, a piston engine, and that as we climb in altitude, we're going to lose the density of the air. As we lose the density of air, we're going to lose power. We lose power, we're going to go slower, we can't climb, so we have all these problems. So we're going to fix that. And we're going to fix that with either a turbocharger or a supercharger, which we're going to get into what they are and how they work. We're going to take air, we're going to compress it and push it into the intake system. And that compressed air, we're going to build it back up so it's either more like we've never left the ground or even more than what we had on the ground, depending on the system. All right, and that's all fine and well. So you pump this air into the intake system. And so the airplane or the engine now thinks, hey, great, I'm at 50,000 feet, but I don't know the difference because I've got all this compressed air. Well, not really, because that air is hot. And so you're going to have some losses because of the heat of that air. All right, it's minimal, right? But at a certain point, you keep trying to do this, you're going to get the air so hot that hot air is going to cause detonation, and it's going to cause the fuel to pre-ignite inside of the intake system, which is a very bad thing. All right, so there is one of your limiting factors to turbocharging or supercharging. So when you look at these things and you realize that maybe the turbocharging doesn't really work as well as you thought it would, you have to stop and say, well, they had to kind of cut it off and restrict it because to go any more would cause more problems. So there's some limiting factors to turbocharging and turbocharging. Did I say turbocharging twice? Supercharging and turbocharging. Okay. So that's why we're going to do it, to try and get our power back. So now let's talk about some of our definitions. All right. So within the turbocharging world, it's, like I said, there's many different ways and styles and different definitions that we have to be aware of. The first one we're call it a ground boosted engine. Ground boosted engine. And this is what you'd think a turbocharger is. And that is an engine that has the manifold pressure above atmospheric on the ground. So if you take a non-turbocharged, non-supercharged engine, a normally aspirated engine is what that would be, and you run it on the ground, and it's 30 inches outside, what is the maximum you're going to get in the intake manifold?
29.
29.
All right, so I'm hearing 29. I said 30 and you said 29. Why do I have an inch loss?
There's always going to be some sort of friction or
Air filter.
on the system.
Yeah, there's some friction. I don't want to go with friction is not there's two things that are going to cause that specifically.
Oh, the air filter
Air
and
filter. And
bends in the induction.
Venturi.
or throttle plate. Yep. So Venturi, throttle plate, they are going to create some. So between those two things, we're going to have about an inch loss. But a ground boosted engine, that's an engine that has a MP manifold pressure above atmospheric. Atmospheric, oops, not in, on the ground. On the ground. And it's important that we distinguish it on the ground necessarily. Of course, once we go, because if we didn't specify on the ground, then everything's going to be boosted. So we say ground boosted. All right. So if I were running a ground boosted engine on the ground, I may look over and see 31, 32, 33 inches, or potentially a lot more. Okay, so ground boosted. The other version of that will be a turbo normalized. Turbo normalized, sometimes called an altitude engine. You're never going to hear me use that because I think it's a ridiculous name. Altitude engine. I say turbo normalized because it makes sense to what it is. So a turbo normalized engine is an engine that does have a turbocharger, but sorry, I just wonder what Zeus is doing. It has a turbocharger on it, but it only tricks the engine to thinking it's on the ground. So if it's 30 inches outside, maybe give you 30 inches. You go up in altitude and it drops to 29 inches, it's going to give you 30. You go up to 28 inches, it's going to give you 30. So it just keeps going 30, 30, 30. It never goes above that. So at all times, the engine is going to simply think that it's just on the ground. But of course, now you know what's going to happen is that air is going to get hotter and hotter and hotter because it has to compress more and more and more. And then at some point, it can't keep up. It can't just keep doing that because the air is going to get too hot. And then at that point, we say it's reached its critical altitude. So a critical altitude for a turbo normalized is a spot where it's no longer keeping up with the 30 inches or ground. But you have to think about that. So, okay, so let's say it's turbo normalized, and I know that it's time for break. So it's turbo normalized to say 10,000 feet. Well, that means when it gets to 10,001, it thinks it's at 1 foot. As where an airplane that has just got nothing, it's at 1 foot. It knows it's at 1 foot. I shouldn't say 1 foot, 1,000 feet. So it makes more sense. So you get to 10,001 with the turbo normalized, it simply thinks it's at 1,000 feet, even though it's at 10,001 because it was normalized all the way to 10. And then from there on up, it sort of starts losing its pressure. So I'll write this when we come back, but for now, I'll give you guys the break.